In this session, I'm going to talk about time value of money. So, initially, we will try to understand what is this time value of money all about. I need to understand what is this time value of money all about, and why do we really need to understand it. Then we'll talk about the interest rates. What do you mean by interest rates and what it means to different people? And once we know these two important aspects, then we can very well get into computations, time value of money related computations, where we talk about determination of future values. We'll talk about determination of present values of different kinds of cash flows, and we'll also talk something about annuities. So how all these things can be calculated using our time value of money related concepts. So just let's get started with that as a broad starting point. See, most of the times what happens is we enter into the processes of either saving money or borrowing. And whenever we do that, when I borrow it, let's say I borrow today, but I repay at a later date. And in the process, I'm paying something higher than what I have typically borrowed. Same way, when I'm trying to save something, I'm saving some X today. But when I'm taking this X probably at a later date, I'm getting something more than what I'm typically saving. What does that mean? The value of money differs with time, and every one of us know that whatever the X which we are receiving today is much more than the X that we receive, the same X we receive in future. And the other way of looking at it is the X of today should be equivalent to X plus Y in future. So whatever we are receiving at a future date, a larger amount is equal to a slightly smaller amount as of today, right? So that is what we are trying to find, the equivalence between the cash flows at a future date versus a present date. What is that makes these two cash flows same? What is that probably if I am getting $1,000 after 2 years, what is the equivalent of it today? Is it $900? Is it $920? Or is it $990? Now that is what is being discussed as a part of the understanding of the time value of money. And typically whenever we are dealing in the world of finance, the time value of money becomes one of the most important topics, because the one key thing that we can master once we know the time value of money is the relationship between the different cash flows which are going to come up at different dates. Because in most of the cases, every investment, every borrowing, we deal with different cash flows at different dates. Now, how do I link all of them and how do I express the equivalence relationship between all of them to assess my overall profitability of the investment or overall cost of the loan. So if I am talking of investment, overall profitability of the investment can very well be assessed using the same concept of time value of money. If I am trying to get into the borrowing process, what is the cost of borrowing? Even that is coming out through this time value of money related concept itself. Right? So with that as a base, let's get started into the understanding of time value of money. So the key driver in this entire time value of money is the interest rate. Right, all the calculations, when I say that I have deposited 900 today and I am getting 1000 after 2 years, whatever the additional that I have got is purely because of the interest. Money carries interest with the time. As the time passes, money carries interest. And so the interest rate, in some cases, it could be a known quantity. It is decided at the beginning itself, probably when I am doing a fixed deposit. The interest which I would be getting on my deposit, I would be knowing in advance. But in some cases, it is a completely unknown quantity, or probably it is more of a volatile kind of a quantity as well. So, first of all, the understanding of the interest rates is important, because that is what we would be using in majority of our time value of money computations. So, when I am saying interest rate, we define it from three different dimensions. One, I define the interest rate as the required rate of return. The first definition of the interest rate, I look at it as the required rate of return. So what is that minimum return the investor will expect if he really wants to invest in a particular investment mechanism? What is that minimum rate of return that would be expected by the investor if he wants to invest in a particular investment mechanism? And the second way I look at it is the discount rate. When I use the word discount rate, if I am going to get some X in future, by what rate I should discount it? What should be the cut? What should be the cut that I can really accept? And what is the value, what could be the value of it after discounting this X as of today? Probably X minus some P. So we can very well look at the discount rate, whatever is the cut in the value based on the passage of the time. So interest rates can be looked at from the perspective of discount rate, and sometimes what people in the finance world, we try to use these two words more or less interchangeably. And the third dimension I look at interest rate is the opportunity cost. Sometimes you look at it, I'm saving, let's say $1,000 I have deposited in a bank, versus I have spent today. If I am spending 1000 today, I have lost an opportunity of probably getting 1050 after 1 year. Let's assume if I have spent 1000 today, I have lost an opportunity to deposit that 1000 and get 1050 after 1 year, which means the opportunity cost here is 5%. I have lost the opportunity of increasing my money by 5%, and that is what we are calling as the interest rate. So interest rate could be defined in terms of opportunity cost, whatever is the value that the investor is going to forego because of the action that has been taken. And the next thing is, once I know the definition of the interest rates, we always observe that the interest rates typically change on a regular basis because of the demand and supply being created. Now, who are the suppliers? Suppliers typically are the investors who keep supplying the funds, and the borrowers are the people who keep borrowing the funds. And the typical interest rate, which is driven by the market forces of supply and demand, what we generally see is the composition. The composition of the interest rate goes like a real risk-free rate plus different kinds of premiums being added on the top of it. One being an inflation premium. One, I have a premium for inflation, the typical way the interest rate gets designed. One is an inflation premium. Then I talk about the default risk premium, the premium that comes because of scope of default. Then we bring in a liquidity premium and a maturity premium. So this is how the typical interest rate comes out. Just trying to understand what each of them is. When I say a real risk-free rate, real is a word always comes into picture when inflation is not considered. When inflation is considered, we use the word as nominal. But when inflation is not considered, we are using the word real risk-free rate. And as word is saying, it's a completely the interest rate on a risk-free kind of a security, which in a real world is always difficult to see. Inflation-free world, whatever is the risk-free rate of interest, that is what we are calling as a real risk-free rate. But the major things are, now when I am bringing in the inflation premium, whatever is the average inflation that is going to occur during or over the maturity of the debt. So if the debt is a 3-month debt or a 6-month debt or a 5-year loan, whatever it is, during the maturity of that, whatever is the average inflation that we are going to expect during that particular period, that is what is being added to the real risk-free rate, and only this much alone is called as the nominal risk-free rate. No other risks being added, no other premiums being added. We call that as a nominal risk-free rate. Generally, we see that the government debts, probably a government debt of, let's say, 90-day treasury bills, whatever is the interest rate that is associated with this short period, because the moment I go for a longer period, maturity premium is going to come into picture. So when I am looking at a shorter period government debt, whatever is the interest rate that is available on that, we can equate it to a nominal risk-free rate. And then we are talking about a default risk premium, where non-government, probably the corporate borrowing or individual borrowing, where there is some kind of possibility of failing to pay. Some kind of a possibility of failing to pay or delaying to pay. So whether it is in terms of time or in terms of amount, any kind of failure to pay is associated with a probability of default. So because of that, an additional risk is getting created, and because of that, an additional premium is getting added to compensate the investor with that kind of a possibility of a default risk. Then the third dimension that I am bringing in is the liquidity premium. See, suppose I'm holding one investment, but I want to sell it off. I want to sell it off immediately because I have some need for money. What typically happens is I may be forced to sell it at a lesser value. I may not be able to sell it at an appropriate value if I want to sell it quickly. I may be forced to sell it at a quicker value, which means conversion to cash is not that easy, especially in a shorter period of time. That is what we are calling as liquidity risk, especially where we talk about small issuers of bonds, or small loan takers, or small so wherever they want to liquidate their position, it does not become that easily. The trading becomes very infrequent, and if at all I have to sell it off, I may be forced to sell it at a much lesser price. So that is where if any particular security is having a liquidity risk, even the interest rate associated with that security would reflect that premium for that as well. And finally, we are talking about a maturity premium as well. The longer the time to maturity, probably the volatility of the interest rates is going to be much higher. And because of that volatility, or probably for some time, there is a possibility that the investor is, why should an investor be motivated to invest for a longer period? Why should he block his money for a longer period when he can very well do it for a shorter period? And if there is no additional return that he can get by blocking his money for a longer period, there is no motivation for the investor to do that. So what we typically see is any interest rate we talk of, it is composed of the real risk-free rate, the inflation premium, the default risk premium, the liquidity premium, as well as the maturity premium into it. Alright. Now let's move towards a few calculations relating to the time value of money, where initially let's focus on one single cash flow. So which means it's more like I'm doing a lump sum investment or lump sum deposit today. What is the kind of value that I will get out of it at a future date? So primarily we are trying to link three elements here. One, what we call as present value. What is the amount as of today, typically denoted as PV? A future value of that investment. What is the value on the date of maturity of that particular investment? Then we are looking at the time period, for how many years I am typically investing it, right? N number of years for which I have invested it, and what is the typical rate of return that investment is going to earn during this particular period, whatever we called as the interest rate R. So generally, if I have to find the relationship between these elements, so assume that I am just going to deposit only for 1 year. and the interest rate is generally quoted as an annual quoted rate. Annually quoted interest rate will be there for us. So what we typically see as a relationship is the future value is nothing but the present value times 1 plus R. If I am looking at it as a 1 year kind of a period. Now which means R is the interest that is going to come on the present value, which means if I have deposited 100 bucks now and the interest rate is 5%, which means that there is an annual interest of $5 that is going to come on that 100 investment every year. Now if it is the same 5, that is the interest that is going to come on the same 100 that is deposited every year, such a kind of interest is what we are calling as simple interest, which will be same every year, because the investment amount is remaining the same every year. So just as a term, this 100 is called as a principal amount. That 5 whatever I am getting is the interest, and I have invested it for a 1 year period. But in general, majority of the finance applications, they go not with a simple interest, they go majorly with the consideration of compound interest. What is this compound interest all about? Whatever is the interest that has come, for the next period, we earn interest even on this. So interest on interest is what we typically call as compounded interest. So when I am depositing 100, probably if I go with a simple interest, the interest of 5 is something that gets coming out to me every year. Whereas if I go with compounding, okay, at the end of first year I am getting 5 only as the interest, but at the end of the second year the interest comes on this 100 as well as on this 5. So the 5% is coming on 105, which is more like probably 5.25. And in the next year the interest is coming on all 110.25, which could be slightly more. So what happens is the gap keeps widening with the passage of time, where the compound interest starts growing rapidly. The compound interest starts growing rapidly as the time passes and passes, because every year the interest is applied on the interest, and the end result is whatever we are receiving at the end of the maturity period, which is a longer period. It's going to be quite significantly different compared to what we get from a simple interest. So that becomes a very powerful tool in the world of finance or in the world of investment. The compounding really creates wonders in terms of we looking at what is the future value we can expect if we have invested or deposited something today. So taking with that kind of an aspect, probably if I just want to showcase a simple example of the same, taking a simple example of the same, let's look at it like this. I am depositing 100. So probably let me call the present value is 100. Let's say the annual rate of interest is somewhere around 8%, and I am looking at an investment period, let's say of 20 years. So if I go with a simple interest mechanism, what is that I am going to receive? Every year the interest is 8% of 100. So 8 is the interest every year. Interest per year is going to be $8, which is 8% of my present value. So interest per year is going to be something around 8, and we are talking about a 20-year period. So interest per 20 years is going to be 8 times 20, which is 160. So total amount after 20 years is going to be 100 plus 160. So whatever the 100 I am depositing, I will be receiving 260 at the end of 20 years if I am going with a simple interest mechanism. But the compound interest works slightly differently. In case of compound interest, because the interest is applicable on the interest, the way we try to relate the future value with the present value is present value times 1 plus r to the power number of periods. So the future value comes as the present value times 1 plus r to the power n. So here we can directly get the amount after 20 years. Amount after 20 years in case of compound interest is going to be the present value times 1 plus r to the power n. So this is working out to almost 466. You see that there is a great increase in the time in the amount. So just that interest on interest has created another 200 odd bucks just with the compounding with time. So as the time period keeps increasing, what we typically see is the amount that is getting generated through the compound interest increases quite drastically compared to the amount that is generated through the simple interest. But in this context, a few things that we need to understand. Whatever the time period, we have used R, we have used number of period. These two should be compatible. When I say these two should be compatible in all our questions, if I say this interest rate is an annual rate, this should be in number of years. If I say the interest rate is a quarterly interest rate, then n should be in the number of quarters. So the period, that is why we say this is a periodic interest rate and n is number of periods. We will not talk in terms of years or months specifically. Whatever is the period here, this should be in the similar number of periods itself. So the time units for both of them should be more or less should be the same. The time units for the interest rate as well as the number of periods, that should be the same. Now, majority of the times, whenever we are using this formula, Fv equal to Pv times 1 plus r to the power n, what we typically call is this 1 plus r to the power n, we generally call it as a future value factor. Because the present value is incremented by this much for computing the future value. And few important points that we need to keep in mind is when I have to add two monies, it's basically like if I have to say I deposit 1000 today, I'm getting 200, let's say after 1 year, I'm getting 200 after 2 years, like that let's say I'm getting 200 up to 10 years. Now to find out how much I have got, it's not correct to talk about adding up all these times, all these amounts which are actually occurring at different points in time. The important rule is I can add two amounts only if they are at the same point in time. If they are at different points in time, they need to be brought to one single time, either to the present or to the future, and only then they can be added. So one important thing in this entire logic that we need to be comfortable with, and with this formula we could very well see, as n is increasing, as n keeps increasing, means the time value keeps, as the number of maturity period keeps increasing, the future value increases drastically. And at the same way, if r keeps increasing, we see that the future value is also increasing drastically. So the typical way we can work out is, as r increases or n increases, we see that the future value is going to increase only, right? So as a numerical, as we have seen, at any time if I am simply doing one single lump sum investment and I am looking at the amount after a particular point in time, the easier way to find it out is using this relationship of PV multiplied by 1 plus R to the power n, right? Now, sometimes what happens is, we may have a scenario where the deposit is not happening today, but probably it's going to happen at a future date, right? Probably it's like I'm going to deposit $1,000 after 1 year, and after 1 year, let's say the interest rate would be 8% per year, and I want to withdraw it, let's say after 3 years. So which means actually if I look at my timeline, this is today, I'm depositing it here, which is 1 year from now, and I'm withdrawing it 3 years from now, which means my investment period is only 2 years. So my future value will typically, if I shift myself from today to this date, saying that this is the present value, if this is the present value, probably my future value here becomes the present value times 1 plus R to the power 2 only, because I am talking about 3 years from now, which is 2 years after the deposit date. So we need to be slightly comfortable with respect to when the deposits are typically being made, what is the time period between the deposit period to the withdrawal period, so that the numbers and the calculations can be done quite comfortably. That's one more important aspect that we need to consider. Now, a slightly different dimension comes out. Majority of the times, till now, whatever we have considered, right, I have deposited for 20 years. The interest rate is 8%. So I have said the future value is the present value times 1 plus R or 1 plus 8% to the power 20. Now, in majority of the case, so here the R whatever we are talking of is the annual interest rate. But in majority of the real world finance applications, the money is, or the interest payments happen, they don't happen once in a year. The interest payments happen much more frequent intervals. So sometimes they can happen on a monthly basis, sometimes they can happen on a quarterly basis, and that is what we call as quarterly compounding, or probably monthly compounding, or some such kind of a word, depending on what period the interest payments typically happen. That is the compounding frequency that we talk about. Majority of the times I may see monthly, which means the interest is deposited 12 times in a year. If I say quarterly compounding, probably the interest is deposited 4 times in a year. So, but whatever is the frequency of the compounding, from typical financial institutions or banks perspective, the interest rate that they publish is what we call as the stated or quoted annual interest. Irrespective of the frequency of compounding, whatever they quote is the annual interest rate. So probably if they are saying 8% is the stated or the quoted rate, if they are doing it as a quarterly compounding, then the interest rate becomes 2% per quarter. So the compounding becomes 2% per quarter, and number of quarters is n. Number of quarters will become 4. So what we typically see is, whatever the rate they quote, it's not, when they say 8% quoted rate with quarterly compounding, what we are going to get is not, the future value is not 8%, the future value could be slightly different from 8. Because the periodic interest rate is what will be 8% divided by 4. If the same is a monthly compounding, then the periodic interest rate will be 8% divided by 12. So, as a definition, the stated or quoted annual rate is nothing but it's a periodic rate with a simple multiplication, no compounding. Periodic rate multiplied by number of periods in a year. Because for a consistency purpose, it is quoted as an annual rate itself. So which means the simple logic of linking it, if at all the compounding frequency is different, is lesser than a year, right, 2 times, 3 times, 10 times, whatever it is, if the compounding frequency is more during a year, the future value formula gets changed to present value times 1 plus whatever is the stated or the quoted rate divided by the number of compounding periods, number of periods in a year, to the power of number of periods in a year multiplied by number of years. So this is what will become the future value in case the compounding happens at a much more frequent intervals of time. So probably better to illustrate, if at all the same amount I want to look at with quarterly compounding instead of annual. This was an amount which is with an annual compounding. But now let's say I want to go with quarterly compounding. What is that is going to happen? The present value times 1 plus whatever is the quoted rate. Quoted rate or stated rate is not going to change. It's an annualized rate. But I divide that with the number of compounding periods in a year. When I say quarterly compounding, there will be 4 compounding periods in a year, to the power of 4 compounding periods in a year, and I am talking about 20 years. So what happens is, if a quarterly compounding is being done, the same amount is going to be 487, almost $21 higher for the same $100 deposit. So as the frequency of compounding increases, probably just to see if the same becomes a monthly compounding, what I typically see is the amount will become the present value times 1 plus quoted rate of interest divided by 12 to the power number of compounding periods in a year multiplied by the number of years. So this is taking me to 492, another $5 extra. So that is how the compounding frequency will typically impact my future value at any point in time. But always remember, whatever is being quoted by the financial institutions, that is not the periodic rate. Financial institutions do not quote the periodic rate. Do not quote the periodic rate. They always quote the periodic rate multiplied by number of periods, which is the stated annual rate. So I have to really convert it as per the frequency of compounding. So again, that's where probably whatever I am taking, that should be the periodic rate, and this should talk about the number of periods per year. That consistency we have to keep as a part of our calculations. So that's one dimension. Now there could be a possibility where for some finance applications we talk about even higher frequency of compounding. Even a higher frequency of compounding. For example, right now we talked about compounding quarterly, compounding monthly. Now I can take it to even such an extent compounding daily, compounding hourly, compounding secondly, millisecondly, and that is where I talk about almost a continuous compounding. Continuous compounding is almost infinite times computed in a year. Very large. All these are typically called as discrete compounding periods, because the compounding or the interest payment typically happens after a particular period of time, after that amount of time has elapsed. But if this is becoming more and more infinite, just to showcase the scenario, when we talked about a discrete compounding, future value multiplied by 1 plus stated rate of interest by number of compounding frequencies to the power of number of times in a year to the power n, number of years. Now assume that this m is becoming closer to infinite. So m is tending to infinite. This is becoming present value times limit m tends to infinite 1 plus rs by m to the power mn. People who remember the concept of limits, it can very well be written as present value times e power rs times n. So whatever is the stated rate of interest multiplied by stated rate of interest is always annual, multiplied by number of years. That is what will give me the future value in case I am going with a compounding, continuous compounding kind of a mechanism. So just the same logic if I have to evaluate here. If I am going with continuous compounding, how much am I going to get? So here it is present value times e power the stated rate of interest multiplied by the number of years. So this is going to be 495. That is the maximum that I can get, and that too in a continuous compounding only. That is the amount that I can get if the stated rate of interest is 8% and I am talking about 20 years being the time period of investment. So just to showcase Now what I wanted to really showcase is for different periods, right? Here I would like to showcase for different periods. Let's say we are talking about the same 8%. When I am saying the annual compounding, the same 8%, what does it work out to? Or semi-annual compounding, or a quarterly compounding, or a monthly compounding, or probably a continuous compounding. Now what is happening in all these things? If I am talking about the same 8%, what is that I am going to get for the same $1 investment? So if I am talking about $1, I am looking at, okay, number of compounding periods. Let me put compounding frequency. We know that here the compounding is happening 1 time in a year, 2 times in a year, 4 times in a year, 12 times in a year, and almost infinite times in a year. So based on that, if I look at the value after 1 year for a $1 investment, I can very well look at it like present value, which is 1 times 1 plus whatever the rate of interest. This is the rate of interest divided by the number of compoundings in a year to the power of compounding, number of times compounding happens in a year. So here I am going to get 1.08 and probably 1.0824, 1.083, and this is where I can talk about e power 8%. Here I'll get e power 8%, which is 1.0832. So this is how we could see that different compounding frequencies, the same stated 8% interest rate could give me different amounts. Here if I am getting just 1.08, here I am getting 1.0816, whereas here I am getting 1.0832. So with the same stated quoted interest rate for a different compounding periods, I am getting completely different amounts. So this is what will lead us to understand another important concept, which is effective annual rate of interest. Versus the stated rate. Now stated rate will be 8% in all the scenarios of the earlier example. But what we are actually getting is much different from the stated rate in all these cases. And this is what we typically call as the effective annual rate. So in this case, the effective annual rate for me is within the 1 year, 1 has become 1.08. So I will take it as 1.08 minus 1. So almost 8%. In this case, the effective annual rate is still 8%. Whereas when I go with all these, the effective annual rate, because at the end of 1 year, I am getting at the rate of 8.16% extra. Though the stated rate is 8%, but what I am really getting is 1.0816 at the end of 1 year, which is equivalent to 8.16% interest. The same logic here, I am getting 8.24, 8.3, 8.33. And these percentages are typically called as effective annual rates. So the 8% stated could be 8% effective annual rate if it is annual compounding, 8.16% effective annual rate if it is semi-annual compounding, 8.24% effective annual rate if it is a quarterly compounding, and 8.33% effective annual rate if it is a continuous compounding. So that's the kind of a relationship that we need to be comfortable with. And in short, whenever I talk about the effective annual rate, I look at it like 1 plus the periodic interest rate right? Probably it's like 1 plus periodic interest rate comes from stated interest rate by m to the power number of periods in a year. Number of periods in a year minus 1. That will become my effective annual rate. Or in case of continuous case, what does it happen? E power, this 1 plus rs by m to the power m will become e power rs, e to the power of stated interest rate minus 1 will become my effective annual rate in case of continuous compounding. In case of a discrete compounding, depending on the frequency of the compounding, my effective annual rate will become 1 plus rs by m to the power m minus 1. So, only when there is annual compounding, only in case of annual compounding, we see that the stated rate is same as effective annual rate. In all other cases, we find that the effective annual rate will be greater than the stated rate. As long as the frequency of compounding is, as the frequency of compounding increases, or if the compounding happens lesser than a year, at less than a year time period, we'll see that the effective annual rate will definitely be more than the stated rate of return. And so one more simple logic. Now that I know effective annual rate is 1 plus stated rate by m to the power m minus 1, I can very well try finding out what is s. Once I have an EAR, probably I can find out s also, because the logic goes like 1 plus EAR is equal to 1 plus rs by m to the power m. So taking to the power 1 by m on both sides, 1 plus EAR to the power 1 by m is equal to 1 plus rs by m. Taking 1 to the other side, rs by m is equal to 1 plus EAR to the power 1 by m minus 1. And from here I get the stated rate of interest is m times 1 plus EAR to the power 1 by m minus 1. And if I want the periodic rate, probably I just need to get the m also down. So this is the periodic rate, 1 plus EAR to the power 1 by m minus 1. And this will be the stated rate, wherein I multiply the periodic rate with the number of periods in a particular year. So this can very well be executed even if it is with a continuous compounding. If I have defined EAR is e to the power of rs minus 1, 1 plus EAR will become e to the power of rs, and rs will become log 1 plus EAR. The moment I am taking the logarithm of 1 plus EAR, that is going to give me the stated annual rate of interest. So for example, if for the same 8.33%, I want to find out what is the stated annual rate of interest, I'll take simply the logarithm of 1 plus EAR. So this is giving me again 8% back. So I should typically be comfortable in terms of converting from one form to other, because different financial institutions, different financial instruments will be priced differently in all these situations. Their compounding frequencies could be different. So understanding the relationships is much more important in all the situations. All right. Now, till now, whatever we have looked at is a single cash flow or a kind of a lump sum deposit. But in some cases, we talk about a series of cash flows, not just one single lump sum. We talk about a series of cash flows, which means at different periods of time I deposit something. So probably I may deposit 1000 now, I may deposit 2000 after 1 year, I may deposit 3000 after 2 years. So different deposits, probably all of them, let's say for a time period which is the same. Probably if this is deposited for 10 years, this I deposit for 9 years, this I deposit for 8 years, but all of them are maturing after 10 years from now. So if that's the case, I'm more interested in finding out what is the future value of all these various deposits that are being done. So that is what we call as a series of cash flows. And how do I find out the future value associated with them? So whenever we talk about a series of cash flows, we have two important dimensions there. One we call as annuity, which is even cash flows, same cash flows. So basically a same amount and same gap in the time period. These are called as annuities. Whereas on the other side, we can very well talk about uneven cash flows, something like this, 1000, 2000, 3000. Whereas when I am talking of annuity, probably same amount at same intervals of time. So there could be two different scenarios, uneven cash flows, which are more common in nature, but even cash flows, which are treated as annuities. Now within this annuities also, there are actually two major classifications. One is called as an ordinary annuity, the other one is called as annuity due. One common factor annuity is we are going to have the same amounts at same gaps in the intervals of time. But if the first payment, if the first cash flow happens one period from now, which is the next period, not now. The first cash flow or the first payment is happening one period from now, we call it as ordinary annuity, or the first cash flow is happening immediately, we call it as an annuity due. That's the major difference between these two. The first cash flow happens one period from now here, the first cash flow happens immediately here when I talk of annuity due. And these annuities generally are for some number of years, some specific period of time. But if this annuity is for infinite period, right, is forever, never ending kind of cash flows. There are some instruments where they keep paying a fixed amount forever, even for generations that cash flow can be received. Those kind of annuities are typically called as perpetuities. So perpetuity is that kind of a cash flow which happens different amounts, same amount at equal intervals of time, but the time period is not specific. Time period is infinite. It's a never ending kind of stuff. So if that's the kind of a scenario, look at it like this. If I want to find out the future value in that case, it's like the same amount A. Let's say I'm talking about a same amount A. I have deposited, let's say 1 year from now. So first A, let's say I have deposited 1 year from now. Another A I have deposited 2 years from now. Another A at 3 years from now, and so on. And so if I have deposited 1 year from now, typically it is like it would be deposited for n-1 years. This would be deposited for n-2 years, because I want to find out the value at the end of n years from now. So this would be deposited for n-3 years. So it's as good as saying the future value is the first one, A 1 plus R to the power n-1, A 1 plus R to the power n-2, plus so on. The last amount a 1 plus r to the power n minus 3, and finally the last one a 1 plus r to the power n minus n. So overall, if I am looking at, if I am taking out a into 1 plus r out, so it is typically coming out as, right, here I can't take the 1 plus r because there is nothing here. So if I am taking out 1 plus r to the power n minus 1 plus 1 plus r to the power n minus 2, we can use the geometric progression kind of formula, sum of n terms of a geometric progression, which comes out as a 1 plus r to the power n minus 1 by r. So this particular thing is what we call as future value of annuity. Future value of annuity factor. So probably just to explain the situation, in this example, if let's say instead of depositing 100 as a lump sum today, if I say the 100 is deposited at the end of every year, 100 is deposited at the end of every year for 20 years at the same 8% interest. Then what is the accumulated amount at the end of 20? That is what we call as annuity. I am depositing 100 at the end of every year for 20 years. So 100 I am depositing after 1 year, another 100 I deposit after 2 years, another 100 after 3 years, and so on, another 100 after 20 years. So if I am looking at all those deposits, and all those deposits mature at the end of 20 years from now, what is the future value? So that is what I talk about, the present value times, I use the annuity factor 1 plus r to the power n minus 1 divided by r. So I'll take it as 1 plus r to the power n minus 1, this entire thing being divided by r. So which is going to give me that I would be receiving 4,576 at the end of 20 years if I keep saving $100 every year for a 20-year period without withdrawing anything in the middle. If I keep saving $100 every year for a 20-year period, it would, assuming an 8% per year interest rate, it is going to accumulate to 4,576. So that is what we can accomplish using an annuity kind of a mechanism. And in case the cash flows are completely uneven, so only when the cash flows are even, we call them as annuity, even in terms of amount as well as even in terms of timing. But whenever they are uneven, either in terms of amount or in terms of timing, we can't use the annuity factors kind of a formulas. We have to typically compute the future value of each. We have to compute the future value of each of the cash flows separately to a particular future time period. And if all of them are computed towards the same time period, then I can add up all of them and I can say that this is the amount that I am going to get in future. So probably it's like, if I am depositing 1,000 now, I am depositing 2,000 after 1 year, 5,000 after 3 years. Now, if I deposit this for 10 years, I deposit this for 9 years, I deposit this for 7 years, then all of them are maturing at the end of 10 years only. So the value, the future value, I compute it at the end of 10 years from now. For this also I will compute the future value exactly 10 years from now. This also the future value exactly 10 years from now. Then all I can do is I can add up all of them and say that this is the overall future value of these uneven cash flows occurring at different points in time. So this is the important thing, especially computing the future values, one of a single lump sum cash flow, two the different a series of cash flows where we look at annuity as a factor in one case, where the even cash flows, even periods of time, whereas the other side is completely uneven cash flows. But in all of them the end logic is the same. I can add the future values only if all of them belong to the same time period. If this 1000 has been deposited for 10 years, 2000 after 1 year for another 10 years, then obviously I cannot add the two future values, because this is the amount after 11 years, this is the amount after 10 years. I cannot add these two amounts. Only when the time periods are same, the amounts can be added. That basic concept still needs to be kept in mind. Alright. Now that till now we have focused on computing the future values, let's divert our attention now to the computations of present values. To a large extent, there is a relationship which we can visualize in our previous computations of future value with respect to the present value, because we have always linked future value equal to present value times 1 plus r to the power n, or we said future value equal to present value times 1 plus stated rate of interest divided by the compounding frequency raised to the power of the number of compounding periods multiplied by n. So in all the cases we had a situation where we computed the future value from the present value, which means the other way, when I have to find out the present value, all I can think of is just an adjustment of the formula. Future value, if I have to compute the present value, it is just a small mathematic or basic arithmetical change that is coming up, right? So this particular, where we are reducing the future value by a certain amount to obtain the present value, in this context the R is being used as a discounting rate. So initially whatever we discussed about the different forms of interest rate, if I want to compute a future value from present value, the R that we use, we call it as a compounding rate or the required rate of return. Whereas when I am looking at computing the present value from future value, the same R gets the name of discounting rate, because I am discounting the future value to give me some value for the present. So that's where we call this particular formula as the computation of the present value from future value, and this particular element 1 by 1 plus r to the power n are sometimes being written as 1 plus r to the power minus n. So this is what we call as the present value factor. Just like the way we said 1 plus r to the power n is the future value factor, 1 plus r to the power minus n becomes the present value factor. And another quick observation, the present value factor and future value factor are reciprocals to each other, right? Just a quick observation out of this. And similarly, even if I am changing the frequency of compounding also, the same result is going to come out. So in this case, I'll say the present value factor, if the compounding frequency is different, I call it as 1 plus rs by m to the power minus mn. This is what is going to be the present value factor. So this is one, and once I look at this equation, I am able to see some interesting points in this equation. If I am looking at the n, the amount coming up at after a period of n years, and as n increases it becomes larger and larger, means if I am going to get some amount after 20 years or 30 years, after a very long period of time, as n increases, as the maturity period increases, if I am going to get some amount A at that point in time, the present value of it becomes smaller and smaller. So as n increases, as n keeps increasing, which means if the discount rate is constant and I am receiving the amount at a very farther period of time, the present value of that is going to be much lesser. Similarly, as the discount rate increases, as n increases, the present value decreases. Similarly, as the discount rate increases, the present value decreases. So this is one more important relationship that we need to understand in this process. And even if the compounding frequency changes, these relationships hold true. As the number of time periods are increasing, the present rest of the things not changing, the present value is going to go down. As the R is increasing and rest of the things remaining constant, still the present value is going to go down. So these are some of the important things as far as the present value of a single lump sum cash flow is concerned. The same logic I can apply to finding out the present value of a series of cash flows. And when I am talking of a series of cash flows, as we have defined earlier in future value also, we have situations of annuity and we have the situations of uneven. Now I don't think I need to define annuity again. Series of equal amounts with equal spaces of time. So those are what we are calling as annuities. And these annuities sometimes could be over a small period of time or over very larger periods of time, or in some cases even over infinite periods of time. So depending on how the payments are being made, we may be interested in finding out the present values of all of them. So if I am looking at the present value of an annuity, here we have to see, is the annuity an ordinary annuity or an annuity due? Why we need to really bother about? Let's say I am talking about receiving a payment A. Receiving a payment A for 10 years. Right? So when I go with the timeline, saying this is 1, 2, 3, 8, 9, 10. Now in case of ordinary annuity, the payments of A are going to come something like this. At the end of 1 year, at the end of 2 years, at the end of 3 years. But if the same is an annuity due, the first payment is going to be right now. So at the end of 1 year, or at the beginning of the first, at the beginning of the second, which is at the end of the first, end of the second. So the A is going to come only up to here, which means the payments are slightly faster in this case compared to this. Right? And as we have just now discussed, as n is going larger and larger, the present value is coming lesser. So what we typically observe is the present value in this case will be slightly lesser compared to the present value in this case. Right? So that is the reason we really need to understand whether the payment that we are, whether the annuity that we are trying to find out the present value Is it for an ordinary annuity or for an annuity due? Let's try out. I'll try to use some formulas from the spreadsheet directly. Let me assume I'm going to receive 1000 every year. I'm going to receive 1000 every year. In Excel, we typically call it as recurring payment or PMT. I'm going to receive 1000 every year for a 10-year period. And let's say the annual interest rate that is applicable in this case is 8%. Now, if it is a regular annuity or ordinary annuity, which is typically called as, the present value of it comes out with, let's say, an interest rate of 8%, the number of periods of 10 years, and every period the amount being received is 10, and the end of the period payments, which is like a regular annuity or ordinary annuity, what I see is the present value of it is somewhere around 6,710. The present value of 1000 being received. So probably how did it work out? If I just want to know, I am getting A at the end of 1 year. So the present value is A by 1 plus R. I am getting another A at the end of 2 years, 1 plus R squared. I am getting A at the end of 10 years, 1 plus R to the power 10 or N. Let's make it general. Now, I can very well find the sum of n terms of a geometric progression, which gives me the first term multiplied by the common ratio. The common ratio is 1 by 1 plus R. The common ratio to the power n minus 1 divided by the common ratio minus 1. So this is what comes out in this case. So just a simplification, A by 1 plus R, 1 minus 1 plus R to the power n divided by 1 plus R to the power n, and this becomes 1 minus 1 minus R divided by 1 plus R. So obviously if I take this out, so it is coming A multiplied by 1 minus 1 plus R to the power n divided by 1 plus R to the power n into minus R. So just take the minus sign out, it comes to out as 1 plus R to the power n minus 1 divided by R times 1 plus R to the power n. Right? Other way of simplifying it, 1 minus 1 by 1 plus R to the power n divided by R. A multiplied by this one. So this is what is going to be the present value. So I could have used the formula directly, but I can use it here like this. A, which is my annuity amount, multiplied by 1 minus 1 by 1 plus R to the power n. This entire thing I am dividing it by R, which is going to give me the same amount, 6710.08. So this particular expression here is called as the present value of an ordinary annuity factor. But the same logic, if I go with an annuity due, I am going to get A now. So there is the present value is just A itself. I am going to get A after 1 year. So like that I am going to get my 10th payment just after 9 years. So overall, now if I look at, if I am taking A out, or probably the sum of n terms. Here I am getting it at the term of n minus 1 years itself by nth payment. So the first term multiplied by common ratio to the power n minus 1 divided by common ratio minus 1. The same logic going again. So a times 1 minus of 1 plus r to the power n divided by 1 plus r to the power n divided by 1 minus r by 1 plus r. So overall again the same simplification, a times 1 plus r to the power n minus 1 divided by r times 1 plus r to the power n minus 1. Only n minus 1 is the only difference that is coming up here. The denominator, there is one decrease of 1 by 1 plus r. Rest all is happening in the same way. So which means it's otherwise, when I try to simplify this, it is becoming a times, this is 1 plus r minus 1 by 1 plus r to the power n minus 1 divided by r. So 1 plus r minus 1 by 1 plus r to the power n minus 1. So the other way it gets simplified, look at it, 1 plus r minus 1 by 1 plus r to the power n minus 1 divided by r. So this is what is coming out, wherein I'll typically take my PM, the annuity multiplied by that. So this is giving me 7,246, which means even if I am going with the formula kind of an approach, I will take the interest rate is 8%, number of periods is 10, the annuity payment is 1,000, but this time the payment is happening at the beginning of the period, which is resulting in 7,246. So that is how we typically see the difference between annuity due and regular annuity. Or in other way, if I am dividing this ordinary annuity or regular, if I am dividing this annuity due by 1 plus r, if I am dividing this annuity due, so the present value of annuity due is equal to present value of ordinary annuity divided multiplied by 1 plus r, or present value of ordinary annuity equal to present value of annuity due divided by 1 plus r, irrespective of and the same logic holds true even if the compounding frequencies change. So the compounding frequency is changing, I get the present value of ordinary annuity times 1 plus rs by m to the power m, right? So this is the kind of relationship between ordinary annuity and annuity due. So that kind of clarity has to be there. Or the other way of simply looking at annuity due, if I am looking at annuity due, probably I'll break it off into the current amount, which is the present value. There is one payment which is the present value, and the remaining 9, so the present value of n minus 1 future payments. So basically it's like the current payment plus ordinary annuity for n minus 1 years. That is what is coming out as annuity due as well. So though there are a total of n payments, one is the current payment, and the remaining n minus 1 payments behave as if it's an n minus 1 period, an ordinary annuity. So I can very well break the problem into a lump sum today, one lump sum today plus ordinary annuity for n minus 1 periods. So that's one more interesting part that we need to be looking at in this case. But doing all this exercise is from a one single perspective. If I have to compare two investments, the easier way to compare them is both of them we need to bring it to the present value. Two different investments will have two different cash flows, different sets of cash flows at different points in time in future. So if at all I have to compare which one is better in the entire process, I have to get all of them to the present value. The comparison can happen only if the time periods of all the cash flows are the same. So if I am able to get all the future cash flows to the present value by doing an appropriate discounting, then that is where I am trying to bring the comparability in the different cash flows. For example, I just want to see if getting some 20,000 bucks lump sum today, I want to evaluate whether getting 20,000 bucks lump sum today is better or 2,000 every year for 20 years. Which one of these two is appropriate? Is it like getting 20,000 today is good enough? 2,000 every year for 20 years is appropriate, assuming that the interest rate is 8% per year. Which of these two options I should prefer? When I say that, I really can compare them only if both of them are working out to the present value. This is nothing but a present value because I am getting 20,000 today, but this is not. I can't say that overall I am getting 40,000 in this case, so that's where this is much more better compared to this. That comparability cannot happen. If these are the different amounts that are coming up, why not look at the present value of this entire investment? So if I am getting 22,000 every year for 20 years at 8%, okay, I am getting 2,000 every year for 20 years at 8%. What we are seeing is the present value of the ordinary annuity is just 19,636. 19,636. If it is an ordinary annuity, what I am getting is only 19,636. So getting 2,000 every year for 20 years, assuming that the annual rate of interest is 8%, the equivalence of this is just 19,636, whereas here it is 20,000. Which means though I am getting 40,000 in essence in total, the value of it as of today is only 19,636, which means it's not worth going for this option. Better you should choose this option. That's where the common problem comes with almost all investment decisions. The comparability can happen only if I am bringing something to bringing all different kinds of investments which have different kinds of cash flows occurring to the present value only. Only if I am able to bring both the cash flows to the same time period, that is where I can compare them effectively. Here you see a trap, right? We are under the impression that we are getting double in the second option, almost 40,000 over a 20-year period. But what is typically happening is the present value of it is just 19,600. Probably you could have got the same 40,000 here as well. You deposit this 20,000 even at 7%, 8% interest. for 20 years, at the end what you may be getting is much, much more. So any comparability can happen only when both of them are being treated at the same timeline. Generally, we compute the present values of the different kinds of future cash flows that can come up, and that is where the comparability happens, right? That's one important point. Now just look at this situation. So I would like to see, let's say we will now decide a timeline. Let's say we are looking at a typical pension scheme. I am today. I am thinking that I have to pay pension, let's say after 5 years. I have to start paying the pension after 5 years from now. So this is a timeline of 0. This is a 5 years from now, and probably I may have to pay it up to 25 years from now. And let's say the pension amount is 10,000 per year. Right, here I have to pay 10,000, here I have to pay 10 for all these years. So exactly 5 years from now, 6 years from now, 7 years from now. So what is happening is, if I shift myself from here to here, it looks as if it is an annuity due. The first payment happening immediately, and 25 or 20 other payments happening. Assuming instead of 25 here, if I am saying 20 payments have to happen. 20 payments of annuity needs, 20 payments of pension of 10,000 needs to happen. So if I am looking at it starting from year 5, probably at the end of year 24, the entire payments are over, right? So here it looks like an annuity due. So where the amount at the end of 5 years, amount at the end of 6, amount at the end of 25. 5, 6, right? At the end of 24 will be the last payment, if I am talking of 20 such payments. Now, but if I am going here, it looks as if it's an annuity due, 1 immediate and 19 ordinary annuities. So probably in this case, what could have come out is, if I have shifted myself not here but up to here only, 4 years from now, what is happening here? It looks as if the next payment is coming at the end of 1 more year, which means it looks as if it's an ordinary annuity of 20 years. Correct? So if depending on where I am shifting on the timeline, I can treat it either as an ordinary annuity or as an annuity due. Okay, fair enough. So let's say I have to make a payment of 10,000 every year. So I can very well input it. So there is a payment of 10,000 every year that needs to be made, assuming an interest rate of 8% per year over a 20-year period I have to make. So I really need to find out what is the amount that it is accumulating to here. How much amount needs to be accumulated here so that these all payments can be made quite comfortably. What should be the present value at this particular point in time? So if I have to find the present value at this particular point in time, then I am looking at it as an annuity due. So the present value at 5 years from now, all I am going at is a computation of the present value using the interest rate, the number of periods that I have to pay 10,000 every period, and this is an annuity due. So if I have the present value of it at the end of 5 years from now is 106, but if I am trying to position myself at the end of 4 years from now, then it is an ordinary annuity. So in that case, at the end of 4 years from now, if I have to see PV at 4 years from now, then I can treat it as an ordinary annuity only. So going at 8% for a 20-year period, payment of 10,000, and here looking at the first payment coming at the end of the one period from now. So here it is coming out to 98,181. Now at the end I want the value as of today. So if I want the value as of today, this has to be discounted by 5 years, this has to be discounted by 4 years. So this becomes this divided by 1 plus r to the power 5, which is giving me 72. This I'll take as this divided by 1 plus r to the power 4. Both of them are giving me the same amount. So whether it's only the conceptualization of a problem that is more important, I can very well take the problem as either an annuity due or ordinary annuity, but the clarity in terms of how that classification, so where do I need to shift myself on the timeline if I am treating it as an ordinary annuity, or where I should shift myself if I am treating it as annuity due. That clarity needs to be there in our understanding. So basically in all these kind of situations, some of the challenging things for us always is, for any kind of cash flows, how do I compute the present value? How do I compute the future value? How do I link the present value with future value depending on the kind of compounding frequencies, what kind of time periods are being looked at, and at the same time keep a track on the calendar. Are the payments happening right away, or are they going to happen at some other future time period? So shift yourself on the timeline. Understanding of the timeline, moving along the timeline is very much important in terms of understanding this particular concept. Then the next important thing which I can look at is perpetuity. We have discussed earlier the definition. Any perpetual annuity is what we call as perpetuity. So the payments happen for an indefinite or infinite periods of time. Typically the examples are like the dividends on stocks. They can happen for infinite period of time. So the concept of perpetuity may come into picture. Some government bonds, they may pay per perpetual period of time, no fixed time periods. Or preferred stocks, they make the dividend payments for a perpetual period of time. So valuing all these things will typically require the understanding of perpetuity as well. So in that case, if I want to find out the present value of the perpetuity, just looking at A coming after 1 year, A coming after 2 years, A coming after infinite years. Sum of infinite terms of a geometric progression. The first term divided by 1 minus the common ratio. So which comes out as A divided by 1 plus R, 1 plus R minus 1 by 1 plus R. So it's coming out as A divided by R. A is that annuity amount and R is the annual rate of interest. So this will give me the present value of a perpetuity in almost in a real world scenario. So this is an expression giving me the present value of the perpetuity. So I can directly use it to compute If at all there is a perpetuity which is paying equal payments of some A forever, then I can find out the present value as that much. But remember, the future value does not exist for a perpetuity because there is no period. Right? There is no period, infinite period. So there is nothing that I am going to get at there because I cannot define the time period there. I cannot decide on how much I am going to get at a future time period at all. So in case of perpetuity, there is nothing called a future value computation. Right? So that's one more thing that we need to be comfortable with. And one more thing, probably if I am looking at a perpetuity, which is the present value as of now, or the present value of perpetuity 4 years from now, or some X period in future. The difference between the present values of these two is same as the present value of ordinary annuity for that much period. Again, one more relationship. If I see in this case only, just the same example, right? In this case, if I am talking about a perpetuity, PV of perpetuity now, PV of perpetuity now is coming out as this divided by R. So this is the present value of the perpetuity. PV of perpetuity 5 years from now. So even at that point, my calculation will still be 10,000 starting 5 years from now. So it's becoming the same 10,000 divided by 8%. But if I have to know the present value as of now, then probably all I am doing is I am dividing this by 1 plus R. I am discounting it by 5 years. So this to the power 5. So this is giving me a value of 85,072. If I take the difference in the perpetuities of these two time periods, which is 39,927, all I am saying is if I am talking about a 5-year annuity from now to 5 years, which is the payment of 10,000 coming after 1 year, 2 years, 3 years, 4 years and 5 years. So I am looking at PV of ordinary 5-year annuity for the same numbers. What is it coming out? If I am using the present value, the interest rate, number of years is 5, 10,000 is the payment, and this is an ordinary annuity. So which is exactly working out to 39,927 itself, which means the straightforward way is if I am trying to find out the present value of current annuity, current perpetuity minus the present value of projected perpetuity for a future point in time, where the perpetuity is starting to happen at a future point in time. The subtraction of this two is exactly coming out to the present value of ordinary annuity for the difference between the two periods. This is one more dimension that we need to be comfortable with. Then, what if the cash flows are uneven? As we have discussed even with respect to future value, if the cash flows are uneven, it's better that I find present value of each of the cash flows by discounting it by the corresponding interest rate, by the corresponding time period, find the present value of each of the cash flows, add them up and say that that's the total present value. So generally when the number of periods and number of cash flows are different, probably a spreadsheet is much more useful. So if I just want to know, okay, at different periods of time, So after 1 year I'm going to get something, after 2 years this much, after 3 years, after 4 years, after 5, after 6. Let's say these are the amounts that I'm going to get at different points in time, and interest rate in the process, let's say, is 8%. It means that I'm discounting each of these cash flows separately, 1 plus r to the power n. So I'm discounting each of these cash flows separately. So each is a separate present value. And finally, when I add up all of them, that is what is going to be the total present value in the process. So the total present value of all these. So if I look at in reality how much cash I am receiving over a 7-year period, I am receiving some 363,000, but when I am discounting that to the present value at the rate of 8%, it is worth only 290,000. So whenever the cash flows are uneven, the best advice is compute the present value of each of them separately and finally add up the total. That is what will give us the total present value, or sometimes we'll at a later point I'll even introduce to a concept called NPV, the net present value, based on the future cash flows that we are typically getting. So especially if the cash flows are uneven, that is a kind of a process that we can follow to find out the present value of our total investments. Alright. Till now, whatever we have looked at is either solving for future value when we had a present value given, we had R given, we had number of periods given, or we had PMTs given, which is the annuities being given, or we had computed the present value when a future value R, N, and probably a PMT, which is the annuity given. But in some cases it might be very much possible, in some business scenarios it might very much be possible that both PV and FV are available, but I may have to compute the interest rate during this process, right? Or in some cases I may have to compute the number of periods, or in some cases I may have to compute the annuity amount. So how do I get into all these kinds of processes? Straightforward again. Probably let me take a few examples which can help me out with that. If I say you deposit 10,000 bucks today, probably I'll create a scenario. Deposit 10,000 today and you will get 18,000 after 5 years. So what is the annual interest rate in this process? Right, depositing 10,000 now, getting 18,000 after 5 years. What is the annual interest rate? So if I look at it, future value is bounded by the present value into 1 plus r to the power of n. The other way I can put it is future value by present value is 1 plus r to the power n. And if I just even more simplify, future value divided by present value to the power 1 by n is 1 plus r, and from there I can get my r as future value by present value to the power 1 by n minus 1. So if I am saying, okay, you deposit 10,000 now, I'll give you 18,000 after let's say 5 years. If I want to know how much is the annual interest rate, so in this case my present value, because I am depositing, it's a cash outflow of 10,000, and the future value is going to be 18,000, the number of periods is going to be 5, and in this case if I want to find out the interest rate, I can use an Excel based formula called rate, where I say the number of periods is 5, there is no annuity payment, whereas the present value is 10,000 and the future value is this much. So overall it is saying that the interest rate in this process is around 12.47%. That could be achieved even through this concept also. Future value, which is 18,000, divided by present value, which is 10,000, to the power 1 by 5 minus 1. So even this is giving you the same 12.47%. So either I can take a help of Excel based formula, or probably I can depend on the formula of future value divided by present value to the power 1 by n minus 1. That is what is giving me the interest rate per the period. In some cases, for these kind of examples, the interest rate is even called as the growth rate. So the annualized growth rate, the other way I can put it up is the annualized growth rate for this kind of an investment example is 12.47% per year. So it's as good as saying the present value multiplied by 1 plus 12.47% to the power 5 is going to give me the future value only. So it's just one single number which takes annually what is the kind of a growth rate that this particular investment is giving. So it's an excellent summary. Typically what we talk of as this particular growth rate is, it's an excellent summary measure of growth over a particular period of time. Over 5 years we are registered a growth of 12.47% per year. So that's the way out to go forward and interpret the growth rate or the interest rate over a particular period. Then I could even have the scenarios where I may have to evaluate the number of periods. Sometimes a simple example, if the current interest rate is, let's say, 9% per year, how many years will it take for my money to be doubled? How many years will it take for your investment to double? Very simple scenario, right? So when I am looking at it, FV, the same relationship, FV equal to PV times 1 plus R to the power n. Now I can very well write FV is nothing but twice PV, because we are talking of it as doubled. PV times 1 plus R to the power n. So just basic arithmetic, 2 equal to 1 plus R to the power n, and it becomes n equal to log 2 to the base 1 plus R. Otherwise it's like log 2 divided by log 1 plus R. This will give me the number of periods that it will take for my money to be doubled. So time to double my money, right? If I just look at this, log 2 divided by log 1 plus R. Log 2 divided by log 1 plus R, which is, let's say, 9%. So this is working out to 8.04 years. The same logic, probably if I am using my formula, I can use NPER, number of periods, assuming an interest rate of 9%, no intermediate annuity payment, and I am looking at a present value of some $1,000 being deposited, and I am looking at it becoming 2,000. All it is saying is the time period that it is going to take is around 8.04 years. So that is one way I can work out my periods. And as we have seen, there are so many real world examples, especially if I want to see in how many years something is going to meet. Probably solving per n is also an important aspect in the same equation. Then the other dimension that we need to focus on is how do I solve for the annuity amount? So through a spreadsheet, especially this is a very critical kind of a mechanism. This is a very critical example wherein we have to compute the annuity amounts, especially if we look at the mortgage payments or some kind of pension amounts. They all work like annuities, more or probably insurance premiums. They all work more or less like annuities because I'm paying equal amount or I'm receiving equal amount at equal intervals of time, and hence majority of them get treated as annuities. So if that's the case, how much should be that annuity amount? So I should be able to have a mechanism to solve what is the annuity amount in each of the cases. So just let me take up or probably just a quick example. Let's say I have taken a loan. I have taken a loan of 300,000 for a 20-year period, and the interest rate is 10% per year. The loan interest rate is 10% per year. I have taken a loan for 20 years and I have to pay equal monthly installment in this case. So if that's the case, what should be that equal monthly installment that I need to pay? This is a very straightforward classic example. So here I am looking at the PV because I have taken a loan currently. The PV is 300,000. Then I have taken it for a 20-year period. N is 20 years. But because I have to compute the EMI, which is a monthly installment, I'll take the N in terms of months, which is 240 months. 20 years multiplied by 12 gives me 240 months. Then the interest rate per year is 10%, but I want it as per month because we are talking about EMI. So 10% divided by 12 becomes my monthly interest rate, and based on this I can very well compute the annuity amount, wherein I am trying to compute PMT, where the rate is this much, the number of periods is this much, the PV is this much. So overall it says that I need to pay $2,895 per month for this loan. So the annuity is getting computed through this kind of a mechanism in a straightforward manner. Now, one simple way for us to work out. I'll take one single example which can demonstrate a lot of things for us. Let me talk about a person X. The current age of the person is 22 years, and the retirement is planned. Retirement age is 63 years, which means 41 years still there from a working perspective. Now there is an expectation that for the next 15 years, let's say the person can save 2,000 per year. Right? Let's try to bring in so many problems into one single. So the next 15 years the person can save 2,000 per year. But at the same time the person is thinking that on retirement right from 63 years, right, on retirement, it is the person is looking at that he wants around 100,000 per year for at least 20 years. The person requires 100,000 per year for 20 years. Now my challenge is, how much does this person really require to save from 16 years to 40 years? How much should this person save from 16 years to 40 years so that this goal is met? And in this process, assume that the interest rate is 8% per year. Now, this accomplished, once you are able to solve this kind of a problem, probably your understanding of the time value of money is becoming completely comfortable. Because if you see here, let's start right now. We are at time 0, where the age of the person is 22 years. Now, from here, let's say to 15 years. From here to, let's say, the 15 years, every year, at the end of the every year, the person is contributing to 2000 per year. The person is contributing 2000 per year. But from 16 years onwards, I really don't know how much the person will be contributing. And up to 40 years, the same thing. 40 periods from now, we don't know how much the person will be contributing, which is going to be some X. But from 41, where the person is going to retire, and we are looking at for 20 years, so up to 60 from now. So from 41 to 60, the person is looking at having $100,000 each of the years. Right, from here onwards, the $100,000 is required for a 20-year period. And in all this process, we have assumed that the interest rate is 8%. And now I need to find out how much should be the amount at this particular, what should be this X that needs to be contributed so that this goal is met. Correct? Okay, let's try to look at solving this. Now I'll shift myself to here. If I shift myself to here and try to find the present value at this point, then it can be treated as an annuity. The first part, this part, I can treat it as an annuity due, ordinary annuity if I am trying to shift at this particular point in time. Alright, so let's try out that. Let me try to shift. So the first part is 41 to 60 years, wherein I am looking at I require 100,000 per year, which is a PMT is 100,000. The number of years is 20. The interest rate, which is R, is 8%. So I can very well find out the present value here. So the present value up to that particular point, giving me 8% rate, 20 years, and a PMT of 1000 per year. The present value is saying 981,814. So as of this date, 981,814 should be there, should be accumulated, so that 100,000 will be distributed over the next 20 years from there. Now, out of that, we have seen that for the next 15 years, 2,000 per year is going to be accumulated. So I can find out what is the future value of all these, 2000s at the end of 15 years. Future value of all these investments at the end of 15 years. So I am taking the situation of 0 to 15 years, wherein I am contributing 2000 per year for a 15-year period, and let's say the interest rate is still the 8% itself. I can find out the future value at the end of 15 years. So I am going to get the future value at 8% per year for a 15-year period, 2000 being deposited every year. I am getting that the future value is 54,304. Okay, all this is getting accumulated to 54,304. And this as a lump sum can be invested for the remaining 25 years. So at the end of 40, the same amount, at the end of 40 years, I can look at it like a lump sum. So another 25 years, the same amount is getting invested. So what is it becoming? 1 plus R to the power 15, to the power 25. For another 25 years, this amount is getting invested lump sum. So this amount is directly working out to 371,901. So whatever the twos that are getting contributed, at the end of 40 years, their contribution has already mounted to 371,901. This entire amount, by the time it reached 40 years, it has already mounted to 371,901, which means whatever is the remaining contribution, as at the end of 40 years, the remaining contribution, the remaining amount, remaining accumulation at the end of 40. What is that remaining that needs to be accumulated? I need to accumulate still around 609,000 at the end of 40 years. So now what I can very well do is, now keeping this in mind, so if the future value is going to be this much, if the future value is going to be this much, now between 16 and 40, if I have to work out, so what will happen? My future value which I have to accumulate is going to be this much. The number of periods, for me is 25, right? Number of periods for me is 25, and the interest rate is going to be 8% for those periods. So based on that, I can very well compute the PMT. If I am computing the PMT at that particular point, taking 8% per year for a 25-year period, with the present value being this, it is working out to some 57,000. Let me just look at this calculation. If I have to do a PMT, the interest rate is 8%, the number of periods is 25. Oh, this is the future value, not the present value. The future value is going to be something like this, which is telling me 8,342 needs to be contributed every year, so that I can take the total value to 609,000. So right now for the next 15 years, though the contribution is 2,000 per year, but from 16th year onwards, the contribution need to be raised to 8,342 per year to meet the goal of getting 100,000 every year for a 20-year period after the retirement. So that's how we can very well work out we need to understand the concepts of the future value, present value, determining rate, determining the annuities. All these combinations of understanding will be required to solve these kind of real-time problems quite comfortably. Now, one more important scenario that I want to look at is, how do I relate for a series of cash flows? How do I relate the present value and future value scenario? Let me just take one simple example. Right? How do I bring the equivalence between the present value and the future value? Let me just assume 5 different cash flows. right, coming at the end of 5 different periods. Let's say randomly I'm giving some numbers, 5 different cash flows, 5 different periods of time. Let's say the interest rate is 8% fixed in all the cases. So I'm trying to find out the present value of all these cash flows. So 1 plus 8% to the power 1. So I'm finding out the present value of all these cash flows. For me, the total present value is working out to this number. Similarly, I am finding out the future value of all these cash flows. So because I am depositing it after 1 year, this will be invested over a 4-year period. So that way, the second one will be invested over a 3-year period. So that way, if I am trying to find the future values of each of these cash flows, so the first one will be deposited at the rate of for 4 years, the second one for 3 years, the third one for 2, the fourth one for 1, and the last one for none. So if I am looking at the total future values also, this is what is coming out to total future value. Now, if I try to discount this total future value to the total present value, 1 plus 8% to the power 5, I am getting the same total present value. So basically, either I compute the total future value and then discount that total to the present, or if I compute the total present value and compound it to the future, both of them will give me the same solution, same result. But one point, the most important in all these situations is the cash flow additivity principle, which we have been discussing for quite some time. I can add the cash only if they belong to the same time period, or unless I index it to a same period. Either I get all of them to the same time period by getting a PV or FV. Unless I index all the cash flows to the same point in time, same time period, I cannot add those cash flows. So in this case, I cannot add these amounts at all. The only way is either I convert them to the present value and add them, convert them to the future value, add them, because they are all at the end of 5 years. They are all as of today. Either I can add them by converting them to the present value, or I can add them by converting them to one single future date. These are all at the end of 5 years. And after that, I can again discount them to get to the present value. So this is a very important thing that we need to keep in mind. And once we have got a hold on all these various concepts that we have looked at, just to summarize, initially we started off with the understanding of the interest rates. Then we looked at finding out the future value and the present value computations, both for a single lump sum as well as for annuities, as well as for uneven series of cash flows. And at the same time, we have extended not just computing future values and present values, how we can try to solve the equations for the number of periods, how we can solve it for the rate of interest, how we can solve it for the annuity payments, all these kinds of different solutions, and how we can integrate all these into a complex real world problem. All these have been considered, and finally looked at the equivalence between finding out the present values and future values, how a series of present values added and a series of future values added, how well they can be linked. So understanding of this entire concepts of time value of money will really play an important role in solving many finance related decision problems. All right. So if you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.